Looking at the Dirac field, the complete set of solutions. So let's just remind ourselves of the Dirac equation. So we have I gamma mu, E mu psi minus M psi is 0. And we're looking for solutions of the form. So QPR into the minus I of P dot X over the square root of a normalization volume, VPR e to the plus I P dot X over the square root of the normalization volume, where the U's and the P's are constant spinners. So they're four-component spinners, constant spinners, in other words, independent of X and T, or in other words, they're independent of the space-time position X. So if we plug that into the Dirac equation, it must be that these constant spinners satisfy gamma mu P mu minus M U P R is 0, and gamma mu P mu plus M times V acting on VPR is 0. These are matrix equations. Matrix equations for U and V. There are no derivatives in here. I just have. So this is a 4x4 matrix whose entries depend on the here P is equal to let's write it as P0 P or PP. P is the square root of M squared plus mod P squared. So you can easily verify that in order for this plane wave to be a solution of the Dirac equation, the components of the momentum have to satisfy the usual relation between the energy and the magnitude of P. So you should check that. You should check that. You're going to need to use probably the fact that gamma 0 squared is 1. Anyway, check that. You ought to just check that this is correct. Go through this, check that this kind of solution is a solution of the Dirac equation. So it's just like plugging in a plane wave into the Klein-Gordon equation, except it's a bit more complicated because there's these four-component spinners that are independent of X. Plug them into the Dirac equation, show that it requires that the energy or the zeroth component of the momentum vector satisfies this relation, and that U and V satisfy these matrix equations. Now, for a given representation of the gammas, you can find the U and V. The U and V are just four-component column vectors whose entries depend on the energy and momentum. And if you're interested in examples of U and P for specific representations of the gamma matrix, as I said, have a look in the appendix in the book. All we're going to need actually are what are called the orthonormality properties of U and V. So something to note that the U is often called, you'll often see this terminology, positive energy solution. V is often called a negative energy solution. Now, for our purposes, this is just because, well, the sign of the energy appearing here is like positive and negative frequency, positive and negative energy. But actually, historically, it's something that is probably good to know about, but maybe best not to go into at this stage, is that historically the Dirac equation was discovered before it was understood in a quantum field theory context. As I mentioned before, Dirac thought he'd found the, quote, relativistic Schrödinger equation. And he was trying to interpret this Dirac field as a wave function, as a probability field, as a probability amplitude, as in quantum mechanics. And the problem you get is that there are negative energy solutions. These solutions here have negative energies. So there was a problem that there was no ground state. The particle can have arbitrarily positive and negative energy. And Dirac came up with this idea called the hole theory, where he said that the grounds, what we think of as the vacuum, actually all the negative energy states are filled. There are particles there in the vacuum occupying the negative energy states, and it's filled. And when you have an extra positive energy state, that's an electron. If instead one of the negative energy states is empty, that appears to be like a positron. And it's called the Dirac hole theory, and it is pretty contorted. It's not the standard view today. The standard view is that was just a historical mistake, really. The Dirac field is something that you quantize, and when you quantize it, you don't get this kind of problem. You just automatically get two different kinds of excitations corresponding to electrons and positrons and particles with equal. They always have positive energies and the equal and opposite charges, and we'll see how that comes up. But anyway, just beware this terminology that you'll come across. Anyway, so what we have, remember here, did I mention, maybe I should not have mentioned, that R is an index 1 or 2. So for each energy, there are 4 independent solutions. For a given, for each of these kinds of solution, there are 2 solutions. Okay, R is an index 1 or 2. What does this index correspond to? R is 1, 2, it corresponds to spin. To see this explicitly when we look at the eigenvalues of the spin operator. But for the moment, what we're interested in is the sense in which we have a complete in the sense in which these form a complete orthonormal set. And we want to choose a convenient complete orthonormal set. So again, the analogy with the epsilon KRs. CF the epsilon KRs for the electromagnetic field. So for each K, we have an epsilon K1 and an epsilon K2. It was convenient to choose these to be normalized and orthogonal to K. And remember, we had these form a complete orthonormal set for expanding the vector potential. You remember we did that way back. Now the choice of the epsilons is arbitrary. I could take any 2 epsilons in this plane as long as they're orthogonal. It's just a matter of choosing a convenient set of solutions in terms of which I can expand the vector potential. So what is a convenient set of solutions here? Convenient set, or a convenient, well, when I say convenient set, this condition here that we have doesn't fix the epsilons, okay? Any set of epsilons that is orthogonal to the k's will do. So we're interested in, well, what kind of properties do we need for U and V in order to have a good, complete orthonormal set? So here is a convenient set. So what people consider is, on All right, remember we defined remember we saw that the intrinsic spin vector is given by an integral over space of psi dagger h bar over 2 sigma psi, where sigma was the following vector matrix where sigma mu nu is defined in terms of the commutator of the gamma matrices. Now, something that is commonly used is to consider the following. If you think of this as being a bit like the spin operator or the spin matrix that you're normally used to, it isn't really the actual spin operator. Is when we convert psi to an operator, this is going to become the spin operator. But just thinking heuristically, you think, well, if this is a bit like the Pauli matrix, this is a bit like the sort of spin matrix that you're used to. So consider the following. Consider this matrix sigma p, which is equal to the component of this vector matrix in the direction of the momentum. So what we do is we choose U and V to be eigenstates of sigma p. So from the heuristic point of view of the spin matrix that you're used to, this means that they are eigenstates of the spin along the direction of the momentum. And it will turn out that when we look at single particle electron and positron states, that they are indeed eigenstates of this spin operator, but taking its component along the direction of momentum. We'll come to that. We'll do this properly. But just to give you an idea, why are we doing this? Why are we choosing U and V to be eigenstates of this matrix? It's because it then turns out that the single particle states that come from the creation operators are eigenstates of the spin operator along the direction of momentum. So these are sometimes called longitudinal spin components. It just means the spin is parallel or anti-parallel to P. So it's a convenient. What you tend to do when you're looking at the Dirac equation. So okay, it's not something I should have said. So in the low energy theory that you're used to, you're probably used to considering, okay, let's pick an axis, the z-axis, and we're going to consider spin eigenstates up or down the z-axis. Okay. It turns out to be more convenient when you do the relativistic or the high energy Dirac theory. Instead of choosing spin along the z-axis, it's more convenient to consider spin along the momentum axis. So I have a particle state with a certain momentum. I say, right, let's take our sort of basic states. Instead of spin up or down the z-axis, there's spin parallel or anti-parallel to the momentum. Okay, so what we do is we choose. So again, it's just a matter of, well, what's a convenient choice? It turns out when you develop the theory, as we're going to do, that this is a convenient choice, just like these epsilons, for the electromagnetic field. So what we do is we choose U and V such that hope it's clear that this is a 4 by 4 matrix, okay? This is a 4 by 4 matrix, this thing. All right, so we choose U and V such that the 4 by 4 matrix acting on UPR is equal to minus 1 to the R plus 1 UPR. So that means for R is 1, U is an eigenstate of sigma with eigenvalue plus 1. For R is 2, the eigenvalue is minus 1. And then for V, we choose it to be almost the same, but minus 1 to the R, which means that the eigenvalues are the other way around for R is 1 or 2. It just turns out that this is more convenient. We'll see later that when we evaluate the eigenvalues of the spin operator along the direction of momentum, you get spin along P when R is 1 and spin along minus P when R is 2, whether you've got electrons or positrons. So it's nice and symmetric. But for the U's and V's, there's a sort of odd asymmetry here. All right, so there is that. Then there is the normalization. The normalization of the U's and V's. You remember when we do the field expansion, there's always some factor in front that is chosen to make the commutation relations for the annihilation and creation operators come out to be what they normally are. It is conventional, you don't have to do this, but it is conventional to normalize U and V such that, just check it on. All right, such that UPR dagger UPR is equal to V PR dagger. VPR is equal to, you might expect it to be 1. You could do that. It turns out it's just conventional to choose it to be E over M. Remember E, so the book puts a subscript P. I usually don't bother. You can use a subscript P if you like. Anyway, E is defined to be the square root of M squared plus mod P squared. The normalization is chosen like this. And the orthonormality relations. Orthonormality relations. You can show, if you're interested, have a look in the appendix or try it yourself. These are the defining equations for the U's and P's, the matrix equations. You can show from those there follow the following orthonormality relations, which again are analogous to saying that for a given wave vector k, the epsilon 1, epsilon 2 are orthogonal to k and orthogonal to each other. It's a similar kind of thing. Here are the orthonormality relations. U, PR, dagger, U, PS equals V, PR, dagger, V, PS equals E over M, delta RS. So in other words, then they have this normalization when the R index is the same, when the R indices are different. They're orthogonal in the sense of this inner product between the row and column vector. Then there's another orthonormality relation between the U and the V, which looks a bit peculiar, but this is what it is. It's U, PR, dagger, with V minus P, S. So U, PR, dagger, V minus PS is 0. So whether R and S are the same, or even if they're the same, this is 0. Now, let me tell you But for those of you who are worried, this Dirac equation, or what do I need to know about this equation? All we're going to need to know is basically the following. All you need to know, really, for the purposes of the quantum field theory that we're going to be doing, all you need to know about the Dirac equation is on this blackboard, plus the statement that these solutions of the form with these conditions form a complete orthonormal set. Okay, so all you need to know, in other words, i.e., you can expand psi, any solution of the Dirac equation can be expanded in terms of these solutions. So if you're worried about, oh, you know, you've got all the experience working with the low energy Schrödinger equation, what about the Dirac equation? Remember, when we quantize the Klein-Gordon field, even the complex Klein-Gordon field, what do we need to know about the Klein-Gordon equation? All we needed to know is that it has this complete set of plane wave solutions. Similarly, for the Dirac equation, all you really need to know is it has this complete set of plane wave solutions, which, with the benefit of hindsight, I mean, at this stage, you think, well, you know, why are you choosing it to be this way? Well, when you construct the quantum field theory, things come out very nicely, as we'll see, and it's because we've chosen these, to label these solutions in this way. We've chosen them to be eigenstates of this matrix, and we've chosen them so that they obey these orthonormality relations, this orthonormalization. So it looks a bit clunky and odd at this stage, but you'll see how everything falls naturally into place when we do the quantization. Okay, so take a mental picture. That's really all you need to know about the Dirac equation is on here. Fantastic. So use your photographic memory, note it down, okay? Plane wave states, but they're with a constant 4-component spinner in front that obeys these funny orthonormality relations, and they're chosen to be eigenstates of this matrix with this funny asymmetry here. But as I said, when we come to look at the actual spin eigenvalues, there is symmetry, as we'll see. All right, so we've got our complete set of plane wave states. Now we can move onwards and upwards and quantize the Dirac field. Okay, so let's do it. We're going to quantize the Dirac field. So, how are we going to quantize the Dirac field? We're going to follow the usual procedure, almost. Remember I warned you at the beginning, there's a slight twist with fermion fields, that there's an anti-commutation comes in, which I'll show you. But for the moment, let's just proceed as if let's expand psi in terms of our complete orthonormal set of solutions of the Dirac equation. So we can write psi, which is of course a function of position in space-time. Okay, let's just write it as if it's a classical field for the moment. What would it be? We're going to expand it in terms of that complete orthonormal set. So our complete orthonormal set is labeled by momenta and the spin index. So we're going to have the sum over P and R. It turns out to be convenient to have an overall factor in front that is M over VE. And then we're going to have a coefficient, CPR. This is a coefficient of the solution. So here's our first, quote, positive energy plane wave states. UPR e to the minus I p dot x plus, we've got the other kinds of solutions. We're going to write the coefficient, so it's an arbitrary coefficient. We're going to write it as D star. It'll turn out to be more convenient. We could just call it D, but it's better to redefine and call it D star. But it's an arbitrary coefficient, and we have VPR e to the I e dot x. So, sum over PR, we've got root m over VE, some coefficient CPR, UPR, e to the minus I p dot x, plus DPR star, VPR, e to the I p dot x. So this is just, we've just said, look, so we've got this complete set of solutions. Here is our complete set of solutions. U times the plane wave, e to the minus ip dot x, v times the plane wave, e to the ip dot x, and we're with a complete orthonormal set, so we can expand always expand the Dirac field in terms of these solutions. The C's and the D star are just arbitrary coefficients. They are just arbitrary coefficients. Now, if you're interested in the conjugate field, which is just psi dagger gamma 0, this is equal to the sum over PR root m over VE. So I have to take the dagger. Remember, this is a 4-component spinner. These U's and V's are 4-component spinners. The C's and D's are just arbitrary coefficients. If I take the Hermitian conjugate, these 4-component spinners become row vectors, and I multiply from the right by the gamma matrix, the 4x4 matrix. So you should be able to see, sort of quite trivially, and then of course, when I take the psi dagger, I also take the complex conjugate. Okay, I also take the complex conjugate. So these coefficients become complex conjugated. Anyway, you should be able to see that this is equal to d PR V bar PR e to the, where V bar is of course V dagger gamma 0, etc. Okay, e to the minus I e dot x plus CPR star U bar PR e to the I e dot x. Okay, that's pretty straightforward. So I've got an expansion for psi and the adjoint field. Now I've written that down. Because, well, that's what the book does. I thought, well, you need it's useful, but not that useful. So I'm actually going to rub this out now because we want to just concentrate on the expansion for psi. Okay, this is just a trivial. If you're interested in the adjoint field, it's just like looking at the complex Klein-Gordon field. You've got an expansion for phi. You take its complex conjugate. You've got an expansion for phi star. Trivial little thing. Never mind too much about that. Let's concentrate on this expansion. Now, so far, all we've said is that the classical Dirac field can be expanded in terms of its complete sets of solutions. Now, let's quantize. Let's now promote the field to an operator. We're going to let this be an operator, and just as we did with the Klein-Gordon field, with these coefficients become operator coefficients. The C's and D's become operators, and D star becomes D dagger. Now, if you go back and you look at the expansion for the complex Klein-Gordon field, you'll notice a resemblance. The complex Klein-Gordon field, the expansion, we had a C times a plane wave, e to the minus ip dot x, plus a d dagger, e to the ip dot x. There weren't the u's and v's because it was a scalar field. So this is just like, so far, it's just like the complex Klein-Gordon field, except we have 4 components. Remember, this is psi hat is an operator with 4 components. Like that, or you could just write it as psi got an operator labeled by an index alpha. Where alpha is 1, 2, 3, 4. Okay, it's a 4-component spinor operator. For each component, the expansion is like the complex Klein-Gordon field. Okay, so now all right, so now here comes the twist. So of course, note the summation here is over the L momenta in my finite volume V, the usual thing, and R is 1 or 2. Okay, so now you might think, okay, it looks just like the complex Klein-Gordon field, except it has 4 components. You might be expecting that we're now going to, well, what you would do, what we did in the complex Klein-Gordon field. So let me just recap for the Klein-Gordon field. At this point, you impose the canonical commutation relations at equal time. Commutation relation between the field and its canonical momentum density. And from those, you find that C the commutators for the C's. You might expect to find the following. We followed the procedure that we followed in other words, I said that so far it looks like the complex Klein-Gordon field, except we have 4 components. If we then continue as if it was like the complex Klein-Gordon field, we would take the canonical commutation relations at equal time, which look like you would have for the alpha component. So if I'm looking at the alpha component of the field, and I would look at the commutator with the canonical momentum density at a different position and at the same time, and this is equal to I delta alpha beta delta 3 x minus x primed. Okay, so if you think of, imagine you thought of this as being like a bit like having four different complex Klein-Gordon fields arranged as a column vector. Okay, and I'm just going to do what we did for each component. I'm going to quantize as we did for the complex Klein-Gordon field. What would you do? You would say, well, okay. What are the canonical commutation relations? Well, for any field, the commutator of a field component with the canonical momentum density is given by this standard relation. So when alpha and beta are different, these commute. So the momentum density for a different field component commutes with this field component. Whereas if it's the same field component, if alpha is beta, then they do not commute at my usual delta function. And what you would do is you would take this field expansion, and of course here in this case, notice that what is pi hat beta, here we worked out from the Lagrangian density, pi hat beta is just I psi dagger beta. Remember, we worked out what the canonical momentum density conjugate to psi, it turns out to be just I psi dagger. So, if we were just going to follow the usual procedure, what would we do? We would take this field expansion, we would plug it into the canonical commutation relations, using this relation between the expression for the canonical momentum density, and from these we would expect to derive these commutation relations, which are, you know, the standard commutation, and let me write etc. here, whereas usually the etc. means that the C's commute among themselves, the D daggers commute among themselves, etc. These are the only ones that are non-zero. And then we'll get the usual annihilation creation operator properties and the usual thing. Okay, if you do that, you get into trouble. If you do that, if you follow the usual procedure, what happens? Now, if you're interested, those of you who are keen, instead of wasting your time at Nick's at the weekend, you might want to figure out the following, that if you do that, you will find that the energy of the field comes out to be the sum over PR E times the number operator. There are two kinds of annihilation creation operators corresponding to particles and antiparticles. That you might expect that the total energy, so the number operator for one kind, so here we have, I should have written this earlier, N, so CPR dagger, CPR. And let's define N bar PR to be D PR dagger D PR. So in other words, these are number operators. Here I've got two types of annihilation creation operators, two types of particles, just like the complex Klein-Gordon fields have two number operators for each type of particle. Note that this over bar has got nothing to do with the psi bar being psi dagger times a gamma zero. It's just this could just as well have been n prime. Okay, just a different kind, a number operator corresponding to the other type of annihilation creation operator. But the book uses n bar. Let's use n bar. Anyway, you might expect to find this, which is what we got for the complex Klein-Gordon field. You've got particles, you've got two kinds of particles. It turns out they have opposite charges, but the energies add up in this way. If you follow this procedure for the Dirac field, something goes badly wrong, which is the following, is you get a minus sign here. You get a minus sign. And so the Hamiltonian, the energy, has no lower bound. So remember, these n's have eigenvalues. So n bar, sorry, I should have written these as operators. These n and n bar have eigenvalues. 0, 1, 2. So I could have states where the energy is arbitrarily negative. There's no ground state. So this is usually considered a disaster. If the energy has no lower bound, then you've got this infinite pit of energy that you could just extract energy from. There would be no oil crisis and all that stuff. So, wrong. Now what we have here, this is an example, something I mentioned, the spin statistics theorem. If you do this quantization, where the occupation numbers can have, you can have an arbitrary number of particles in each state. This is bosonic statistics. what we've actually done is we've quantized the Dirac field according to bosonic statistics. You can have an arbitrary number of particles in each mode. And remember, I mentioned to you earlier on that something goes wrong if you do that. For the Dirac field, the statistics have to be fermionic. Here is what goes wrong. The energy has no lower bound. So we've done something wrong. Okay, how can you fix this? So way back at the beginning of the course, I told you, look, quantum field theory is just quantum mechanics applied to fields, except there's a twist when it comes to fermions. Here is the twist. This is what you've been waiting for. The twist is easy to describe because you're advanced people, you're advanced students, so I can tell you all you have to do, the only change you have to make is turn this canonical commutation relation, instead of having a commutator here, we replace it with an anti-commutator. So, commutator, two operations, is AB minus BA, and the anti-commutator is AB plus BA. So some people like to write this. Sometimes you'll see this notation for an anti-commutator. Don't confuse it with a classical Poisson bracket. But anyway, this notation is also common. But anyway, the book uses this. So you put an anti-commutator. So what happens is in the canonical commutation relation for the Dirac field, the commutator is replaced by an anti-commutator. You say that the anti-commutator of the field with its canonical momentum density is equal to the usual expression. And if now you plug in the field expansion into this, what you might call an or canonical anti-commutation relation, let's call it canonical C plus relation. Okay, the canonical anti-commutation relations. If you plug the field expansion into here, what you find instead of these relations, you find the same thing but with the commutators replaced by anti-commutators. That's what happens. So in fact, what you'll sometimes see in books is that people will say, okay, for fermionic fields, in the canonical commutation relations, you just replace commutators by anti-commutators. This is how you quantize a fermionic field. You then plug in the field expansion and you obtain anti-commutation relations for these coefficients C's and C daggers. The way the book does it is a bit awkward. What it does is it says, let's impose these relations on the coefficients. The book doesn't do this step of deriving it from here, which is a bit unfortunate because there's a nice symmetry really between the bosonic and the fermionic case. The bosonic case, you have your usual canonical commutation relations between the field and the momentum density. And you plug the field expansion into there, and you get the commutation relations for the annihilation and creation operators. Here it's the same thing, except everything's an anti-commutator. You have a version of the canonical commutation relations, but with an anti-commutator. You plug the field expansion into here, and you can derive these results here. Whereas what the book says is, well, let's just impose these relations. Well, it's a bit it's nicer to think of it like this. But at this point, you might think, okay, well, that's all very nice, but surely this is going to completely mess things up, because the usual relations with the commutators give us the nice set of harmonic oscillator states. By a mathematical miracle, it turns out, so let me again write down, let's again define number operators. number operators, so the operator NPR is just defined to be C, PR, dagger, C, PR, and N. Again, this bar is just a label to distinguish that, to note that we've got a different number operator corresponding to these other operators D and D dagger. So you might, usually these have eigenvalues 0, 1, 2, 3. Okay, if I take, when I say usually, I mean without this plus. If I have the usual commutation relations, so these are like the usual harmonic oscillator commutation relations, then you can show that, well, the C's and C dagger, D dagger act like creation and annihilation operators, and I've got an infinite number of energy levels, or an infinite number of levels that correspond to eigenvalues that can be arbitrarily large for the number operators. If instead I have the anti-commutators here, it turns out that now, whereas now eigenvalues are restricted to 0 and 1. That is the effect of these having anti-commutators here. Now, let me just show you quickly how that works. A little detour. So before we continue with our quantization, let's just do a little detour. Let's see. Okay, imagine that we are, maybe leave this here, and let's see if we can justify this. Okay, let's just think about, let's just go back to the usual harmonic oscillator, where we have, let's just label the states by a single index R. Where R can be 1, 2, 3, 4. Then instead of writing the index as PR, let's just write R, just for ease of notation. And let's just understand what's going on here. So think about your usual harmonic oscillator commutation relation for A and A dagger, where you define a number operator to be A dagger A. Now, these relations imply the following, that NR AS is equal to minus delta RS AS, and commutator NR with A dagger S is equal to delta RS A at dagger S. Now these relations, if you go back and you look at your book that you studied when you first did the energy levels for the harmonic oscillator, you will see that these imply the interpretation with creation, annihilation, and number operators. In other words, the results where you have your set of energy levels, where you go up with A dagger, you go down, so A is a lowering operator, A dagger is a raising operator, N has eigenvalues, corresponding to how many how high up you are, all that interpretation, it all comes from this. You can go back and check where all that comes from. These are the crucial relations that give you that interpretation. Now, it turns out that if you have it turns out that if you have instead, and this is something you can check, so I guess you can think of this as a homework problem if you want to go through it. I mean, the first section of chapter 4 of the book discusses this a bit, but it doesn't really go into details. It's something, again, more like a homework problem if you want to verify this, that if instead you replace these commutators by anti-commutators, okay, that's the only change I've made, and I still define the number operator in the same way, you still get these same relations where these are still commutators. It's just a funny, just a mathematical peculiarity that so let me repeat that. If I replace this commutator here, this commutator relation, by an anti-commutator, and I define n in the same way, I still get the same commutation relations between n and s, n and a, and n and a dagger. And in order to show that, you might want to use, so to derive these commutators from the usual commutator is you're going to use the identity. There's an identity that you're familiar with. Okay, there's an identity for commutators that you're familiar with. It looks like this. You will use that identity if you want to derive this from the usual commutator. In order to derive these from the anti-commutator relation here, you're going to use a modified version where this commutator can be written as, here I have anti-commutators, and here there's a minus sign. Okay, this is also an identity that you can check. The commutator of AB with C is equal to A times the anti-commutator of B and C minus the anti-commutator of A and C times B. And using this relation, this implies this thing. So in other words, what we have are these look like the usual harmonic oscillator commutation relations, but with anti-commutators. You might think it's going to mess everything up, but actually you still get the same interpretation of creation, annihilation, and number operators. And the only difference, but there is a difference, the only difference is that, note, if you look at this, remember, of course, we have the etc. That the A, I've written down the anti-commutator A and A dagger. We also have the anti-commutator of the A's and the anti-commutator of the A daggers. Now remember, normally the commutator of the A's is 0, the commutator of the A daggers is 0. Here the anti-commutators are 0. Okay, so it's just the usual relations. The etc. refers to the D's and the C's anti-commuting with themselves. So we have, not only have we replaced this by a anti-commutator, but these the usual relations look like this. The commutator of the A's and the A daggers is 0. We have anti-commutators. What does this imply? If you put R equals S, it implies that AR squared plus AR squared is 0. In other words, it implies AR squared is equal to also A dagger R squared are both 0. The square of the annihilation and creation operators are now 0. So this means, so this is new. This is new. You don't have that usually. This comes from the fact that we have anti-commutators here. The square of the A's or the square of the A daggers are 0. And if you now look at the square of the number operator, which we define to be just A dagger A in the usual way, the square of the number operator, here's something funny happens. It's A dagger R, A R, A dagger R, A R. So I've just squared the definition of the number operator. And remember that the A and the A dagger obey this anti-commutation relation. So this is equal to, I can write this as 1, this middle term, A dagger, I can write as 1 minus A dagger A. All right, I just swapped the order of the middle terms and used this anti-commutation relation. And now notice that, well, here I'm going to get an AR squared, which is 0. So this term here vanishes, and I just get A dagger R AR, which is equal to NR. So in other words, the square of the number operator is equal to the number operator. So let me write down then what that means. If I have NR minus 1 is 0, and so the eigenvalues are restricted to 0 and 1. Eigenvalues are restricted to 0 and 1. Another way to think about this is that, let's say I start with my ground state. I start with my ground state, which is defined by, how is the ground state defined? It's defined by following that the annihilation operator acting on the ground state gives you 0. Okay, the usual thing. Let us now act on the ground state with the raising operator or the creation operator. That raises us up a level. Okay, so we have 1. So the raised level is equal to A hat dagger R acting on the ground state. You might now think, okay, let's now go further up. Let's go further up. Add another excitation. Let's act with the raising operator on this state. Let's act again with the raising operator. Well, that this is equal to the raising operator squared acting on the ground state. Okay? But the raising operator squared is 0. So you've just annihilated the state. So there is no higher state. So there's nothing up here. For each mode, there are just 2 states. The ground state and an excited state. And the fact that you can't have, if you had a higher state, the particle interpretation would be that, well, I have 2 particles in the same mode. But the Pauli exclusion principle tells you, well, I can't have 2 particles in exactly the same quantum state. Okay? So this is where you get fermionic statistics. Now, from the point of view of quantum field theory, what has happened here? You may maybe remember this in the usual quantum mechanics you do. You have symmetrized or anti-symmetrized wave functions. Here, from the point of view of quantum field theory, well, if you quantize with the usual canonical commutation relations, where this is a commutator, you get bosonic statistics, because you plug in the field expansion here, you get these relations where these are commutators, and you get your usual relations with a number operator that has eigenvalues 0, 1, 2, and have an infinite number of particles in each mode. If instead you impose canonical commutation relations that are a bit different, that these are anti-commutators, then you plug in the field expansion, you get these relations that look like usual, except these are anti-commutators, and the result is that, well, the eigenvalues of the number operators are now restricted to 0 and 1. We have fermionic statistics. So the upshot of this, so what have we done? So we've said, okay, we've expanded the Dirac field in terms of our complete set of orthonormal plane wave states. We've promoted the field to an operator. Because it's a fermionic field, we've taken the canonical commutation relation with an anti-commutator, and we get a set of commutation relations, or what we get anti-commutation relations with the C's and C daggers, which it turns out still has, the C's and C daggers still can be interpreted in terms of annihilation and creation operators for two kinds of particles, just like we had for the complex Klein-Gordon field. So we have so C's, the C daggers. We have annihilation and creation operators for one kind of particle which turned out to have one sign of charge. We're going to call them electrons. We're going to identify them with electrons. Finally, you're at the point in physics where this is actually the best description we have of what electrons actually are. These C's and C daggers are annihilation and creation operators for electrons, whereas the D's and the D daggers are annihilation and creation operators for positrons. Now what we're going to do, just as we did with the Klein-Gordon field, we're going to show that when I act on, in other words, we're going to see this shortly. Let me just write. Well, actually, maybe it's a good idea to write this down now. How do we know this? Why? So clearly we have two sets of annihilation creation operators for two kinds of modes. Why do the particles have equal and opposite charge? So just as we did for the complex Klein-Gordon field, let's look at the charge operator. Let's look at the charge operator, which, remember when we were looking at the classical theory, we found just think how advanced you are, how far you've come. The Lagrangian density for the Dirac field is has a phase invariance that implies a conserved charge from Nernst's theorem, which we wrote down. We wrote it as a constant Q. Instead of calling it a constant Q, let's write it as, let's write Q, the little q as minus e. That is minus e. We have an integral over all space of psi dagger psi. This was for the classical Dirac field. The operator corresponding to charge is obtained just by promoting this Dirac field to operator field. So here is the expression for the charge operator in terms of the Dirac field. It is just an integral over all space of psi dagger psi times a constant. Let us now plug in the field expansion. Do the usual thing as you did for the Klein-Gordon field, complex Klein-Gordon field. Plug in the field expansion and you should be able to show that this comes out to be equal. Of course, you're going to have to use the properties of the u's and v's, the orthonormality relations. But you should be able to show that this comes out to be equal to minus e times the sum over all the modes, PR, times the number operator, n, minus the number operator, n bar. So in other words, remember I've defined two kinds of number operators for the two types of particles. The total charge operator comes out to be a sum of one kind of number operator minus the other kind of number operator. So here you have, the, just like we saw for the complex Klein-Gordon field, that the numbers of these particles correspond to different signs of charges. So if I have 3 of these particles and 5 of these particles, the total charge is 3 times the constant minus 5 times the same constant. Okay? So the particles of equal and opposite charge. We have particles and antiparticles with particles with equal and opposite charge. Now, in order to derive that, there is again a slight twist with the fermions. I'm not sure actually, is this necessary here? Anyway, normal ordering. Remember that we defined, in order to eliminate the infinities of the vacuum state, we redefined all our physical quantities. So any observable omega is replaced by the normally ordered version, where the A's are to the right of the A daggers. You should remember way back, I think we did this for maybe the electromagnetic field or the Klein-Gordon field, is you rearrange the order of the A's and A daggers to put the A's to the right. And this eliminates it's just really a trick to eliminate the infinite terms that are associated with the vacuum. Now what happens, there are actually two types of normal ordering. There's the bosonic, where, for example, the normal order, if I had, let me just write, just leave off any indices. If I had, let's say I had an expression AA dagger, and I say let's normal order it. Okay, normal order it, you just rearrange the terms so that A, the annihilation operator, is to the right. So another way of thinking about this is that you swap them, assuming they commute. It's another way of thinking about it. You can say, well, I swap the order and then I imagine they commute. You think of it that way. In the fermionic case, the definition of normal ordering has a little twist, is that, so let me write it like this, as if, so a way to go from here to here is you say, let's swap the A and the A dagger, imagining that they commute. And I get this, there's another way of expressing it, okay, as if they commute. You want the A to be to the right. In the fermionic case, the normal ordering here, there's a minus sign. In other words, you swap the order. For normal ordering, you want the annihilation operators to stand to the right, but when you swap them around, each time you exchange a pair of A and A dagger, you imagine that they anti-commute. As if they anti-commute. So there's that normal ordering. And really, when you define the charge operator, instead of just psi dagger psi, you have the normal ordering of psi dagger psi. So in other words, when you multiply out, you take the field expansion for psi, you multiply by the field expansion for psi dagger, you get all these terms where the C's and the D daggers and the things are multiplied, you have to normal order them. The orderings of the C's and D's have to be normal ordered. In other words, where all annihilation operators stand to the right. But when you swap terms, you treat them as if they anti-commute. So you're going to get some minus signs. So the charge is defined with normal ordering, and it comes out to be this. This is your homework problem. Homework. Please show this. Okay? If you can derive this, you have a chance of passing the final exam. If you can't derive this, you have no hope whatsoever. So, please do this. Remember, what is it you need to know here? You've got this field expansion. The U's and V's are four-component spinors. You need their orthonormality relations. The C's and D's, and C dagger, D dagger, obey these anti-commutation relations. Here is the expression for the charge with a normally ordered, with normal ordering here. We do the usual normal ordering, but when you swap the order of A's and A daggers, or in this case it will be C dagger, C whatever, you treat them as if they anti-commute. So every time you swap a C and a D, or a C and C dagger, you introduce a minus sign. You then multiply these two field expansions, take the normal ordering, integrate over all space, use the orthonormality relations for the U's and the V's. You should find this expression. Please, homework, this is a very important problem. This problem, working through this problem, you'll work through all the mechanics of the spinors, the indices, and the matrices, and the orthonormality relations. It will get it all, processed in your mind. So please do this problem. Doing this problem will help you understand the fundamental nature of the universe. It will also help you pass the final exam. There you go. All right, so if there are any questions, I'm around. If anyone is getting lost, the Dirac field is tough. It's maybe the toughest part of the course. Anyone is getting lost, please email me for an office hour. I'm available anytime. Okay, are there any questions? No questions. Okay, please do the homework. Please do the homework. All right.